Today we're going to create new series from basic Taylor series, and it's really just an extension of what you learned in Algebra 2 of, say, giving you an equation for f of x and then asking you to find, say, what f of x plus 1 is, where you just literally go through and plug in an x plus 1 everywhere you see an x. All right, but to do that, you have to start with a basic Taylor series. So for part A, we're going to find the first four non-zero terms and the general term of the Taylor series for f of x equals cosine x, centered at x equals 0. All right, the general term is not something that we've really come up with yet. However, what that does is it's basically the pattern that you're using so that you could create more terms without having to write out all of those derivatives. All right, so let's just concentrate on writing out the first four non-zero terms for the Taylor series for f of x equals cosine x. When they ask you to create a Taylor series, sometimes they ask you to go to a certain degree, and sometimes they ask you to write a certain amount of terms. So let's just kind of start taking our derivatives and see where we go from that. So f of x is cosine x. F prime of x, therefore, is negative sine x. F double prime of x is negative cosine x. The third derivative will be sine x. And if we were asked to do the fourth degree, then we would know that we just had to go to the fourth derivative. But the first four non-zero terms, I'm not quite sure. So I'm going to stop here and start evaluating all of these at x equals 0, like I have to do to create that formula for the Taylor series. All right, so f of 0, what's the cosine of 0? 1. F prime of 0 is 0. F double prime of 0 is negative 1. The third derivative at 0 is 0. Okay, do you see the pattern here? Yes. Your fourth derivative would be positive 1. And I need four non-zero terms. So f prime and the third derivative are going to be 0 terms, so I can't really count those. So what derivative do I need to go up to? The sixth derivative. Good. And what will that sixth derivative at x equals 0 be? Negative 1. Good. All right, so let's write the Taylor series. All right, so the Taylor series, the first term is f of 0, which is 1. My second term is 0, so everything that would be part of that term cancels out. My second derivative is negative 1, and therefore x to the second power divided by what? 2 factorial, or 2. Same thing. All right, the third derivative is 0. The fourth derivative is 1, so plus 1, and that will be x to the fourth power. Right, the derivative number and the exponent always match. Divided by 4 factorial. And then the next term will be minus 1 x to the 6th over 6 factorial. All right, so that's the first three non-zero terms. Now my general term. My general term is basically that formula that when I plug in n equals 1, n equals 2, n equals 3, I'm going to get all of these terms right here. Well, first off, I know that these are alternating terms, so I'm definitely going to need a negative 1 to a power. Now, it may be n, it may be n plus 1. I'm going to have to come back and kind of check that. All right, then if I plug in n equals 1, n equals 2, n equals 3, n equals 4, what would the exponent on x be in terms of n? If it's x to the n, then I would have an x squared, an x cubed, an x to the fourth, and x to the fifth. But all of my exponents on x are what kind of numbers? Even numbers. 2n. Very good. And then the exponent matches the factorial on the bottom, so divided by 2n, that whole quantity factorial. All right, let's check to make sure that this matches up. First of all, and it doesn't matter what n you start with, it just has to, if you've got to pick a number n to start with that will match this. So should I start with n equals 0 or n equals 1? I'd have to have n equals 0 because I don't have an x term. I just have a constant right there to begin with. So x to the 0 is 1, negative 1 to the 0 is 1, and 0 factorial is actually defined to be 1. So that one works out. If n is 1, I have negative 1 to the 1, which is negative 1, x squared, and then 2 factorial. If n is 2, I'm going to have a positive coefficient, x to the 4th over 4 factorial. So that works. Cosine x is one of the harder ones to come up with that general term, and we're going to practice it, so you're going to see, I think you're going to get good at it, so if you're nervous about that part, don't be very nervous about coming up with that general term, because that is one of the harder ones to come up with that you will see. All right, find the first 4 terms and the general term of the Taylor series for g, where g of x equals f of x squared. Well, I have f of x sitting up here in part A. What would I do to find f of x squared? If in algebra 1, I gave you that f of x equals 5x plus 3, and I asked you to find f of 2, what would you do? Plug a 2 everywhere you see an x. So if I want to find f of x squared, I plug in x squared everywhere I see an x. All right, 1, there's no x in there, so that just stays 1, minus x squared. I'm plugging an x squared in for x, and then I have to square it. So x squared squared is x to the 4th over 2 factorial, plus x squared to the 4th is x to the 8th. X squared to the 6th is x to the 12th. And there's 4 terms. X squared to the 2n power is x to the what? 4n, right. Power to a power, you multiply the exponents. Okay, that's all there is to it. If g of x had equaled f of x cubed, what would I have done? Put in x cubed everywhere you see an x. Okay? All right, C is similar, but a little bit different. I want to find the first 4 terms in the general term for the Taylor series for h, where h of x equals x times f of x. Multiply each term by x. It's really that simple. I know it's hard to believe. F of x is an infinite number of terms, so you have to think about it as x times the whole quantity f of x, so you do have to multiply every single term by x. So 1 times x is x, minus x squared times x is x cubed over 2 factorial, plus x times x to the 4th is x to the 5th, over 4 factorial, minus x to the 7th, over 6 factorial, what would x times x to the 2n be? Right. Add your exponents, so x to the 2n plus 1. Okay, so we're taking a complicated concept like series and just going back to basic algebra. All right, find the first 4 terms in the general term of the Taylor series for k, where k of x equals f prime of x. All right, think back to chapter 2 when we learned to take derivatives. If f of x equaled 5x squared plus 3x plus 2, then when I asked you to take the derivative of that, didn't you just take the derivative of every single term? Okay, that's all we have to do here. The first term for f of x was 1. What's the derivative of 1? 0. Okay, the next term is negative x squared over 2. So what's the derivative? 2x over 2, or just it's negative, so negative x. All right, what's the derivative of x to the 4th over 4 factorial? The derivative of x to the 4th over 3 factorial is 4x to the 3rd over 4 factorial, and 4 over 4 factorial simplifies to 3 factorial. So x cubed over 3 factorial. All right, the derivative of negative x to the 6th over 6 factorial would be negative x to the 5th over 5 factorial, because you end up with 6 over 6 factorial. And I've run out of terms that I've created for part A. However, I need the first 4 terms for part D. So what's the next term going to be? Plus x to the 7th over 7 factorial. And you can get that by either creating the next term on number 1, which would be x to the 8th over 8 factorial, or just following the pattern down here for part D. Okay, now your general term for f of x was negative 1 to the n x to the 2n over 2n factorial. And we need to take the derivative of this. And we're taking the derivative with respect to x. So anything else, like the numbers and the n's, are just coefficients in front of that variable x. So if I take the derivative with respect to x, the 2n comes down in front, right? And then I will have x to the what power? 2n minus 1, and then over 2n factorial. Can I simplify 2n over 2n factorial? Yep, 2n minus 1 factorial on the bottom. No, you do not have to go off to the side and do that. I just wanted to make sure I wasn't losing anybody. All right, well, if we can take the derivative of a Taylor series, then we can certainly integrate a Taylor series. This notation's a little bit different, though, than what you might expect. M of x is the integral from 0 to x of f of t dt, I believe that should say. It's a typo. So what this means is integrate f of t and then plug in an x minus plug in a 0. And after I work this and we see what the final answer is, I'll kind of tell you why they ask it like this, and it's actually easier than it may appear. Integrating f of x would be the same thing as integrating f of t, right? You just have a variable of t. All right, so if you want, you could write out what f of t is. If that'll help, you can do that. And f of t is literally just what we got in part A, but we're using t's instead of x's. All right, so when I integrate f of t, what do I get when I integrate 1? T minus, what happens when you integrate 1/2 t squared? 1/6 t cubed. Okay. So I can do 1/6 t cubed because I've got these factorials over here, or t cubed over 3 factorial, right? I don't care which one you use, but it may be easier to see the pattern when I do this. All right, t to the 4th will become 1/5 t to the 5th, but 5 times 4 factorial is really 5 factorial. So t to the 5th over 5 factorial. And then the next term will be t to the 7th over 7 factorial. All right, when I integrate the general term, my new exponent on t will be 2n plus 1. So when I multiply by 1 over 2n plus 1, that becomes 2n plus 1 factorial. And then I'm supposed to evaluate this from 0 to x, which means plug in the x minus plug in the 0. Well, plugging in the x is pretty easy. Minus plugging in the 0 is even easier because what happens? Every single term is 0. So this is just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 plus negative 1 to the n x to the 2n plus 1 power over 2n plus 1 factorial.